This is a continuation from page 8 of the complex numbers booklet. We're now looking at division of complex numbers, and when we're dividing complex numbers, the process that we use is called realization, or realization of the denominator, meaning here real. In other words, we're going to make the denominator real. So here we can see that our numerator here is a complex number, and so is our denominator. So when we divide complex numbers, we're going to end up with a solution that has a real denominator. So, for example, as I said, looking at this complex number 2 plus I over 3 minus 2i, it doesn't look like the complex numbers that we've seen so far, because we have both real and imaginary parts in the numerator and the denominator. So what we want to do is make this just look like a normal complex number in the form of x plus yi. At the moment it is x plus yi divided by x plus yi. So the process that we're going to use, again, is called realizing the denominator. So for example, if we have a plus bi over c plus di, we can express it in the form of a simple complex number, x plus yi, by multiplying both the numerator and the denominator by the conjugate of this denominator, by the conjugate complex number of the denominator. Now, the conjugate of c plus di is c minus di. So we've got a plus bi over c plus di will equal a plus bi over c plus di times the conjugate of c plus di, which is c minus di over c minus di. And now I'm just going to do that. So we've got a plus bi times c minus di over c plus di multiplied by c minus di. Now expanding out the numerator, we've got ac minus adi plus bci minus bdi squared, divided by, now this is of the form a plus b, a minus b, so it will just be c squared minus di all squared. Now on the numerator, we've got ac. Now this is minus bdi squared. Now I squared is -1, so it will be just plus bd. And these are the imaginary components. So we've got plus, I'm going to do this bit first, BC and minus AD, because I is a common factor with BCI and minus ADI. So there's your real component, imaginary component, over, now this will be C squared minus D squared I squared. So therefore this will be AC plus BD plus BC minus AD I over c squared. Now d squared I squared is d squared times -1, so it will be minus negative d squared, which is plus d squared. And so now we have realized the denominator. The denominator is now real. Okay, looking at our first example here. Express 2 minus 3i over i in the form of x plus yi. Here we've got a division of complex numbers. So this is 2 minus 3i over 0 plus I. I'm going to write this as a in complex number form with our real and imaginary parts. So that's equal to 2 minus 3i over 0 plus I times, the reason I'm writing it like this is because the conjugate complex number of I is 0 minus I or negative I. So it's times 0 minus I over 0 minus I. Now we know that we can just ignore these zeros. So really it's negative I times 2 minus 3I over negative I times I. Okay, because 0 plus I is just I and 0 minus I is just negative I. So on the numerator we've got negative 2I, then we've got plus 3I squared over negative I times I is negative I squared. Now 3I squared is 3 times -1, which is -3, so this is -3 minus 2I, always writing the real part of your complex number first and then your imaginary component second. And negative I squared is -1, which is +1. and so therefore this is negative 3 minus 2i. So this is now in the form of x plus yi, noticing that x is negative 3 and y is negative 2. Okay, next example, expressing the following in the form x plus yi, 4 plus 7i over 2 plus 3i. That's a division problem again. So to do this, we multiply by the conjugate complex number of the denominator, which would be 2 minus 3i over 2 minus 3i. So expanding the numerator, 4 times 2 is 8. We've got minus 12i plus 14i minus 21i squared. The numerator will be 2 squared minus 3i all squared, which is in the form of a squared minus b squared. On the numerator, we've got 8. This will be plus 21, which is 29, and this will be plus 2i over 4. Now, minus 9i squared will be plus 9. So therefore, the complex number is 29 plus 2i over 13. But to write it in the form of x plus yi, remember the 13 is the denominator of this whole numerator, so it's 29 over 13 plus 2i over 13. So this now, where it's written like that, is not in the form of x plus yi. This is because 29 over 13 is my x and 2 over 13 is my y. Now for this last example here, writing 2 plus 3i divided by 1 minus 2i in the form a plus bi, just the same sort of thing again, 2 plus 3i over 1 minus 2i times the conjugate complex number is 1 plus 2i times 1 plus 2i. Expanding numerator, we get 2 plus 4i plus 3i plus 6i squared, and the denominator is in the form of a minus ba plus b, which would be a squared minus b squared. Collating like terms and simplifying here, 6i squared is negative 6, so 2 minus 6 is negative 4. Here we've got plus 7i over 1 minus 2i squared will be 1 plus 2, which, and writing this in the form of a plus bi, it'll be negative 4 over 3 plus 7i over 3. So therefore x is negative 4 on 3 and y is 7 on 3. Mistake there, you've probably already picked it up. We've got 1 minus 4i squared, which is 1 plus 4. So 1 plus 4 is 5. So solution is negative 4/5 plus 7i over 5. So just fixing that up, please. Page 9, multiplicative inverse. Now this is written as z to the power of negative 1. Now we know that z to the power of negative 1 is 1 over z to the power of 1. So this is called the reciprocal. When we take anything to the power of negative 1, we're really finding the reciprocal of that number. We know that a number multiplied by its reciprocal is equal to 1. For example, if we have the number 2, its reciprocal is 1 over 2, and we know that 2 times a half is 1. So our question here is to find the reciprocal of I. So we know that, just looking at what we've done up here, a number times its reciprocal is 1. So we don't know what the reciprocal is for I, but we know that I times x, so let x equal the reciprocal of I. So 1 times x we know is 1. Therefore, x equals 1 divided by I. Now, we can't leave that as 1 divided by I because we need to multiply by the conjugate complex number of I. So remembering that 1 over I means 1 over 0 plus I. So to do this division of 1 divided by I, we need to multiply by 0 minus I, which is just negative I, over 0 minus I, which is negative I again. Now that is equal to, remember this is a 1, so we've got negative I over negative I squared, which equals negative I over negative 1, which is positive 1, which is negative I. So therefore, the reciprocal of I is negative I. Okay, now The multiplicative inverse or reciprocal of a non-zero complex number x plus yi is denoted or written as z to the power of -1. So the reciprocal of a complex number is found by realizing the denominator as the product of complex conjugates is real. So we know that from before that when we multiply x plus yi times x minus yi, we get a real, the product of those two is a real number. So now just looking at this down here, sorry, just focusing here. So the multiplicative inverse or the reciprocal of the complex number z. So z to the minus power of -1 is 1 over z. Now we know that z equals x plus yi, which is 1 over x plus yi. Now we know that we are dividing by a complex number, so we multiply by the complex conjugate, which is x minus yi over x minus yi. Now just fixing this up on your sheet, that therefore is z bar, now just 1 bar, so that's z bar divided by z times z bar. Now, z bar we know, of course, is x minus yi, and we know that when we multiply these two things down here, x plus yi times x minus yi, we get x squared minus yi squared, which is x squared minus y squared I squared, which is x squared plus y squared, which is what we've got there. So just fixing this, there's two little bars here and I just want one. So therefore, the multiplicative inverse or reciprocal of this complex number, so we've got z to the power of -1 is 1 over z, which is z bar over z times z bar. Okay? Okay, an example here. So if 4 plus 3, if z equals 4 plus 3i, find z to the power of -1, or the multiplicative inverse of z. So z to the power of -1 is 1 over z, which is 1 over 4 plus 3i. And we know that that is 1 over 4 plus 3i times 4 minus 3i over 4 minus 3i, which is 4 minus 3i over 4 squared minus 3i all squared, which is 4 minus 3i over 16 minus 9i squared, which is 4 minus 3i over 16 plus 9, which is 25. I'll just write 25 there actually. 4 minus 3i over 25. So therefore, writing it in complex number form, it's 4 over 25 minus 3i over 25. Okay, now, just a little bit more here on real and imaginary parts of a complex number. Real numbers z have no imaginary part, so they have imaginary part of z equal to 0. And imaginary numbers z have real part z equals 0. Now, you're probably getting confused here. Remember, a complex number is x plus yi. So if I just have x, that is real only. The yi bit is the imaginary bit. So when you have a real and an imaginary bit, so this bit's real, this bit's imaginary, but together a real and an imaginary bit make up a complex number. So if I have only the imaginary part, then the real part must be 0. That's what this is saying. So if I just have an imaginary number, then the real part's 0. If I have a real number only, then the y, the imaginary part, is 0. That's what that's saying. So the imaginary part of the number 2, now 2 is the same as 2 plus 0i. So the imaginary part of this is 0i, so the imaginary bit is the coefficient of the I, which is 0. Now the number 3i, the complex number 3i is 0 plus 3i. That's what it is. So the real part of this is 0 as well. Okay? Now, the only number which has real z, this should be an equal sign, equal to imaginary z, which is equal to 0 is the complex number z equals 0, because just watch, if I've got the complex number z is 0 plus 0i, my real part of z is 0 and my imaginary part of z is 0. So the only number which has the real part of z equal to the imaginary part of z, which is both equal to 0, is z equals 0. Okay, page 10. So find the complex number z such that real z equals 2 and z squared is imaginary. Now we know that z equals x plus yi. Now if the real part of z is 2, that means that x is 2. So therefore my complex number is z equals 2 plus yi. So find the complex number z such that the real part of z is 2, which I've done, and z squared is imaginary. Well, I need to come up with an expression for z squared. Now z squared will be 2 plus yi squared. Now expanding this, because this is of the form a plus b squared, is a squared, which is 2 squared plus 2 times a times b plus b squared. And just evaluating this, I've got 4 plus 4yi plus y squared I squared, which is minus y squared. Now, I'm now going to put the bit with the I is the imaginary part, and the bits with no I are the real parts. So therefore z squared equals 4 minus y squared, because they're the real bits, plus 4yi. I'm just going to put those real bits in brackets. So if I want z squared, so if z squared is imaginary only, then there is no real part. Then this 4 minus y squared bit has to equal 0. Now, to solve this, I can either factorize, so I can go 2 minus y times 2 plus y is 0, so therefore y equals 2 or negative 2. So, however, I'm supposed to find the complex number z such that real part of z is 2 and z squared is imaginary. So I know my complex number is z equals 2 plus yi. So therefore my complex numbers are 2 plus, well, y can be 2, so it's 2 plus 2i, or z will equal 2 minus 2i, because this y can be 2 or it can be negative 2. So my two complex numbers are z equals 2 plus 2i or z equals 2 minus 2i. Okay, now next question here. How do we solve quadratic equations with, we're just looking at solving some quadratic equations with real coefficients. We've already done this before, so just a bit of practice again. Use the method of completing the square to solve this equation, this quadratic equation. So we've got x squared plus 2x plus 3 is 0, so I'm just going to take this 3 to the other side. Then we're going to halve the coefficient of b, which is half of 2 is 1, square it and add it to both sides. And so writing this now as a perfect square, x plus 1 squared is negative 9 plus 1. Sorry, that's not negative 3 squared, it's just negative 3. So it's negative 3 plus 1 squared, or negative 3 plus 1, which is negative 2. Now square rooting both sides, x plus 1 equals plus or minus the square root of negative 2. And bringing this negative 1 over, I've got that x, I'll just keep it actually, is plus or minus the square root of, now negative 2, sorry, there's no I there, sorry, that's just a negative 2, square root of negative 2. Now, we know that negative 1 is I squared, so this negative 2 becomes 2I squared. So therefore, x plus 1 equals plus or minus the square root of 2 times I, because it's the square root of 2 times the square root of I squared, and the square root of I squared is I. And taking this 1 to the other side, we've got x is negative 1 plus or minus the square root of 2 plus I. So therefore, remember, we're trying to solve this quadratic equation, and because it's a quadratic with x squared, you expect two solutions, and the two solutions are negative 1 plus root 2i, negative 1 minus root 2i. Okay, so we can use completing the square to solve quadratic equations, or we can use quadratic formula to solve quadratic equations. So I'm just going to do these both with quadratic formula. Quadratic formula is x is negative b, which is x is 2, plus or minus the square root of b squared, which is 4, minus 4 times 1 times 5, over 2 times 1. So it's 2 plus or minus the square root of 4 minus 20, which is negative 16, over 2, which is 2 plus or minus the square root of 16i squared over 2. Now, simplifying this, we get 2 plus or minus square root of 16i squared is 4i over 2. And simplifying this, dividing everything by 2, we've got 1 plus or minus 2i. With this second one here, we do have real coefficients, however, this is a surd, but still the coefficients are real, okay? So this one is x is negative b, which is negative root 3, plus or minus the square root of b squared. Now, root 3 squared is 3, minus 4 times 2 times 1, over 2 times 2. So we've got negative root 3 plus or minus the square root of 3 minus 8 is negative 5 over 4. So this becomes negative 3 plus or minus the square root of 5i squared over 4, which is negative 3 plus or minus the square root of 5 times I over 4. Now, I'm just going to, instead of going over 4 in one go, I'm just going to put each of these over 4, and that way I don't have to write an extra line here. Okay? Now, I know we've done these before, but I just want you to notice something. Notice that in each of these examples above, I end up with 2 solutions because they're actually in all of these, okay? So let's look at this first one. All the coefficients of the x squared and the x and the, so a, b, c, the coefficients in all of this are all real numbers. And look at my roots, negative 1 plus root 2i, negative 1 minus root 2i. They're identical except for this is a plus and that's a minus, okay? Here, I've also got real coefficients of a, b, c. I've got 1, negative 2, and 5. Look at my 2 roots, 1 plus 2i, 1 minus 2i. Complex conjugates of each other. And in my third example, even though I've got the square root of 3 as the coefficient of the x, and here I've got a 2 and a 1, notice I've got 2 solutions for x, and they are negative 3 over 4 plus root 5 on 4i, or negative 3 over 4 minus root 5 on 4i. Again, 2 solutions that are complex conjugates of each other. So notice that in each of the examples above, I've got 2 roots, and they are complex conjugates, and this will always be the case when the quadratic equation has real coefficients and discriminant less than 0. So here my discriminant's negative 2. Here my discriminant's negative 16, here my discriminant's negative 5. So, if a quadratic equation has real coefficients and the discriminant, which is b squared minus 4ac, is less than 0, the roots will be complex conjugates of each other. Now, you really need to know this, because if you don't, when you come to do harder questions later, you're going to be stuck and you're going to think that you don't have enough information, but you do. So, in comparison, a quadratic equation with rational coefficients and discriminant greater than 0 and not a perfect square will have 2 irrational roots that are conjugate surds. So, for example, find the roots of the following. So, here we've got x equals negative b, which is 4, plus or minus the square root of b squared, which is 16 minus 4 times 1 times 2 over 2 times 1, which is 4 plus or minus the square root of 8 over 2, which is 4 plus or minus 2 root 2 over 2, which is 2 plus or minus root 2. If I look at this next one, x equals negative 6 plus or minus the square root of b squared, which is 36 minus 4 times 1 times 3 over 2 times 1. which is negative 6 plus or minus the square root of 36 minus 12 is 24 over 2, which is negative 6 plus or minus the square root of 6 times the square root of 4, which is 2 root 6 over 2. Dividing all these by 2, we get negative 3 plus or minus root 6. So notice here, the discriminant here is greater than 0. So I don't have complex number solutions, but I still have two solutions which are conjugate surds of each other. See, my two solutions are 2 plus root 2 and 2 minus root 2. Okay, here my discriminant's greater than 0. So I have two solutions, and my solutions are negative 3 plus root 6, negative 3 minus root 6. So if your discriminant's greater than 0 and you have real coefficients, you do have two solutions, provided that this, and what we're saying here, if the discriminant's not a perfect square, you'll always end up with a surd in your denominator. But the two roots that you get, they will be irrational roots, because they can't be written. For example, square root of 2 can't be written in the form of a fraction. So they're irrational roots, but the two roots are conjugate surds of each other. What happens up here, the two roots, if the discriminant's less than 0, you will have two roots, but they're complex conjugates of each other, not, okay, so complex conjugates of each other. Okay, so that's the end of the first booklet. The second booklet that you received, the next video, I'll send another 2 additional videos to this. They will go through pages 11 to 15 for you as well.